Let us discuss how to design an hexadecimal up counter. Okay, hexadecimal up counter means the count should start from 0, 0 and it should end at f of h. So here we have the assembler directives, SJMP main, and this assembler directives together with this mnemonic will help us to decide the starting address of program storing. So it is going to start from 30h. Then initially we have cleared the A register. After clearing the A register, so we introduce a delay here. Okay. So this delay is introduced between every count so that we can clearly see the delay on the output. Uh, then what do you have here? After clearing, then after a delay, then we are incrementing it by 1. So this will increment the content of A by 1, and again we call the delay. Okay. So then we check for the maximum value, whether the count reached the maximum value. The count is not reached the maximum value, then what we can do, we can go and continue the increment. As you continue increment, then it will become 2. Like that, it will get incremented. So we are using a delay subroutine here. This subroutine is mainly used to uh, help us to see the counting clearly on the output. Otherwise, the counting cannot be seen properly. Let us execute this and see. So add the file. So from the source group, so we have the file over here. So hex up count is the first one. So we will add it now. Then you can close it. After adding hexadecimal counting file, then you can select the build target. If there is no error, it will be saying 0. Then you can start your debugging. And here the count is going to take place on A register. Okay. So what you can do, you can use this watch window. Then in the watch window, you can have a watch 1 here and click here and press F2. Then again press A now, then press enter. So it is initialized with the value 0, 0, 0, 0. If you run the program, then you will be able to see that the counting is having from 0, 0 to 1, 1, then it will increment to 2, so that we can see the counting clearly. 3, 4, like this the counting will continue to happen. 5, 6, 7, 8, 9. After 9, you will get a in hexadecimal counting. Okay. Now let us see how to see the hexadecimal up down counter. How to increment the hexadecimal up down counter. Okay, after 9 in hexadecimal, you can see that it's going to be A here. Good. Then stop the program, back to the position, and now what we'll do, we'll just see the hexadecimal down counter. In the hexadecimal down, you can see that what do we have here is we have the assembly directives, everything remains same. Only thing is now we are going to start the count from FF, then our maximum value will be 0, 0. So from FF down, FE, FD, like that, it will come down and it will come up to 0. Okay, so that we are going to see that here. So this one we will remove from here. Then after that we will add hexadecimal down counter here. So ASM source and the down program we are uploading it here. Then add it and close it. Then you can right click and build the target. Then there's no error. Then go to debug. So in the debug already we have used A in the watch window, so it will be there. So now if you run the program, the count will start from FF. Okay. Then FF, it will go to FE, then FD, FD, and so on. It will go up to 00H. Then what we can do is, then we can see the BCD up counter. In a BCD up counter, the delay subroutine remains same. Only thing is we do little modification in the main part of the program. So A is initially cleared and we are calling a delay subroutine. and we are, instead of using INC, here we are using ADD instruction, because in a BCD, in order to make the BCD addition a valid BCD number, we are using this instruction, which will adjust the decimal in a way that the sum would be a valid BCD number. That's why the DAA is used here. After that, again, the subroutine is called. Now, if you see the counting will start from 0 and will go up to 9, because that's a valid BCD number. It's a packed BCD, we can say that. Okay. So now let us execute this and see this program. So you can now add the BCD down program, BCD up program, sorry, BCD up program, and add it and close it. Then you can build a target. So as you build a target, then you can start your debugging, and as you start your debugging, you would be able to see that EA is already added here in the watch window. Then run the program. It will start from 0, then it will go to 1, then similarly it will go up to 9. After 9, since it's a decimal counting, after 9 it will be 1 0, it won't be 0A. So how it has happened? It is taken care by this DA instruction. So 4, 5, like that it will continue to execute. 5, 6, then you have, what do you have, 7, then you'll be getting 8, 9, after 9 it will get 1 0, 9 will get 1 0. Yes, that's how you should get the BCD up counter. Now let us simulate the BCD down counter. BCD down counter, what do? We'll initialize the A register with the value 99H, and we call the delay. Since for a BCD addition we use this DA, which is followed by the add instruction. So we add 99 with 99, and DA will convert that into a valid BCD number, so that after 99 you will get 98, then again delay, and again it will become 97. Like that the BCD will do the down count. Okay, let us see the simulation part of it. So now we have BCD down count here. Okay, BCD down count. So add a file, then you can go for BCD down count. So in a BCD down.asm is the file, added it, then build a, so build the target, then you can start your debugging. After starting the debugging, check it out, the value of A is 0, and that is by default will be there. But when you run the program, the initial count will be 99, then it will become 98, then it will become 97, and so on up to value 00H. Okay, that's how the BCD down counting is taking place. So we can use an assembly language program to design a hexadecimal up counter, down counter, BCD up counter, and also the BCD down counter. Okay. Here we will see how to write an ALP to check the operations of byte level logical operations. Okay. So here what do we have? We have the assembly directives, and combination with the SJMP instruction, we decide the starting address of our program storing. So that is from 30H. So here we have used a stack pointer. The stack pointer is loaded with the value 4F, so that when the program gets stored, when the values are getting stored, the stack pointer, if you use the push operation, the stack pointer will be incremented by 1. That means the FF will, from FF it will become 50. Then 50, it depends on the push or pop operation, it will continue to execute. So here we have mostly used the push operation, so that the result will be start storing from 50H. Then what do we have here? The we have the operands stored in 30 and 31H. So from 30H, the values will be moved to A register. From 31H, the value will be moved to with the content of 31H, the content of A will be ANDed. Okay, then the result will be stored in A register. So this content we push it to the stack. How? By using the push operation. Push 0E0H. So what will happen? This 0E0H is nothing but a direct address of A register. So now the stack pointer from FF, it will become 50. So to the 50 H address, the AND operation will be pushed. Similarly, for a 51, the OR operation will be pushed. Similarly, for 52, XOR operation will be pushed. Subsequently, we have XOR, we have a complement, and also we have the RL, rotate left, then rotate left with carry, rotate right with carry, then rotate right through carry, and also swap operations are used here. Okay. So now you can see that here you can build the target and you can start your debugging. And now first what we have to do, we have to give the values here in the A 30 and 31H. So I use two operands, AA, then I use also A CD, let me use A B C D. Okay, and for their convenience, I'll use the calculator also here. So we use the calculator in the programmer mode so that we can able to see the logical operations easily here. Okay, so in the programmer mode of the calculator, I keep it in hexadecimal, and now when I execute this, I'll be able to see the required operation here. Okay, now what are the values I'm given here? I've given AA. Okay, I've given AA operation, AA, and it's a bitwise operation as AND operation, right? So AA, sorry, not AA, it is AB. AB, it is AND operation ANDed with CD. So AA ANDed with the CD. What will be the value? ANDed with CD. That will be 89H. So this 89H now it will be in 50H. You can run the program and you can see that here you have, okay, 89H having the value. The 50H will having the value 89H. Okay, and also you can see that for OR operation. So again for AB is ORed with CD. Then the result will be EF. You can see that the result is EF here. Okay, and like that it's get continually stored in the subsequent memory locations by using the push operations. Okay, now let us see the bit level logical operations. Here we have the bit level logical operations, and here the logical operations will be performed on the bits of a operand of a register. Okay, so here we use the bits called 00H and 01H. So the content of 00H will be loaded to C register, and the content of 1H will be loaded. It's actually bit address. So 1H will be ANDed with the content of C register, which we fetched from here. So whatever the answer, it will be loaded onto 08H. Okay, and very importantly, what you have to understand here is the 00H and 01H are the bit address of a byte address 20H. And when you store this value 08H, again this is also a bit address, but this is the first bit of the byte address 21H. When you see it in the program, you'll be able to see it in the output part. Okay, next what we'll have, then we have the AND operation with the complement, OR operation, OR operation with the complement, like that. Set B operations, okay, and other operations we have here, set B, and also the clear operations. Anything can be executed using this particular bit level logical operations. Now right click and build the target. So no errors. Then you can go for simulation. So the simulation, you can see that the what value we have to load it here. So here I can, as I told you, I'm using the bit address of 20H. So what do? I do it in such a way that the last two digits will be set to high. The last two digit will be set to high, so that I'm entering 0, 3H here. Okay. So last two digit means now when I run this program, so this is for 20, this is for 21. Got it. So when I run this program, you'll be able to see that the last two digit means the AND OR operation will be 1. So if it is the complement operation, it will be 0. So like that, when you decode it, you will be able to see that what is the value exactly it's going to be passed. So it is going to give the value 3DH. It's going to give the value 3DH. So this 3DH, if you decode it, it will be 0011, then 110 1 will be there. Okay. So that indicates that each and every bit, it indicates the result of an operation. Okay. Okay. Thanks for watching.